There is a hole at the bottom of math. A hole that means we will never know everything with certainty. There will always be true statements.
Can I put some fucking AC on it? It's so hot, dude. Just taking a nappy.
That cannot be proven. Now, no one knows what those statements are exactly, but they could be something like the twin prime conjecture. Twin primes are prime numbers that are separated by just one number, like 11 and 13, or 17 and 19. And as you go up the number line, primes occur less frequently, and twin primes are rarer still. But the twin prime conjecture is that there are infinitely many twin primes. You never run out. As of right now, no one has proven this conjecture true or false.
But the crazy thing is this: we may never know. Because what has been proven is that in any system of mathematics where you can do basic arithmetic, there will always be true statements that are impossible to prove. That is life.
Specifically, this is the game of life, created in 1970 by mathematician John Conway. Sadly, he passed away in 2020 from COVID-19.
The game of life is just kind of boring.
Conway's game of life is played on an infinite grid of square cells, each of which is either live or dead. And there are only two rules. 1, any dead cell with exactly 3 neighbors comes to life. And 2, any living cell with less than 2 or more than 3 neighbors dies. Once you've set up the initial arrangement of cells, the 2 rules are applied to create the next generation, and then the one after that, and the one after that, and so on. It's totally automatic. Conway called it a 0-player game. But even though the rules are simple, the game itself can generate a wide variety of behavior.
How's that a game?
Some patterns are stable. Once they arise, they never change. Others oscillate back and forth in a loop. A few can travel across the grid forever, like this glider here. Many patterns just fizzle out. But a few keep growing forever. They keep generating new cells. Now, you would think that given the simple rules of the game, you could just look at any pattern and determine what will happen to it. Will it eventually reach a steady state? Or will it keep growing without limit? But it turns out this question is impossible to answer. The ultimate fate of a pattern in Conway's game of life is undecidable, meaning there is no possible algorithm that is guaranteed to answer the question in a finite amount of time. You could always just try running the pattern and see what happens. I mean, the rules of the game are a kind of algorithm after all.
No, it's not random.
But that's not guaranteed to give you an answer.
You can't even say it's random, because even saying random in computers isn't it kind of a dumb concept? It can't be random. Nothing can be random.
Either, because even if you run it for a million generations, you won't be able to say whether it'll last forever or just 2 million generations, or a billion, or a Googleplex.
It can't.
Is there something special about the game of life that makes it undecidable? Nope. There are actually a huge number of systems that are undecidable, like Wang tiles, quantum physics, airline ticketing systems, and even Magic the Gathering.
To understand how undecidability shows up in all of these places, we have to go back 150 years to a full-blown revolt in mathematics.
In 1874, Georg Cantor, a German mathematician, published a paper that launched a new branch of mathematics called set theory. A set is just a well-defined collection of things. So the 2 shoes on your feet are a set, as are all the planetariums in the world. There's a set with nothing in it, the empty set, and a set with everything in it. Now, Cantor was thinking about sets of numbers, like natural numbers, positive integers like 1, 2, 3, 4, and so on, and real numbers, which include fractions like a third, 5 halves, and also irrational numbers like pi, e, and the square root of 2. Basically, any number that can be represented as an infinite decimal.
I've learned this.
Are there more natural numbers? Or more real numbers between 0 and 1? The answer might seem obvious. There are an infinite number of each, so both sets should be the same size. But to check this logic, Cantor imagined writing down an infinite list, matching up each natural number on one side with a real number between 0 and 1 on the other. Now, since each real number is an infinite decimal, there is no first one, so we can just write them down in any random order. The key is to make sure we get them all with no duplicates and line them up one-to-one with an integer. If we can do that with none left over, well, then we know that the set of natural numbers and the set of real numbers between 0 and 1 are the same size. So assume we've done that. We have a complete infinite list, with each integer acting like an index number, a unique identifier for each real number on the list. Now, Cantor says, start writing down a new real number. And the way we're going to do it is by taking the first digit of the first number and adding 1. And then take the second digit of the second number and again add 1. Take the third digit of the third number, add 1, and keep doing this all the way down the list. If the digit is a 9, just roll it back to an 8. And by the end of this process, you'll have a real number between 0 and 1. But here's the thing. This number won't appear anywhere on our list. It's different from the first number in the first decimal place, different from the second number in the second decimal place, and so on down the line. It has to be different from every number on the list by at least one digit, the number on the diagonal. That's why this is called Cantor's diagonalization proof. It shows there must be more real numbers between 0 and 1 than there are natural numbers extending out to infinity. So not all infinities are the same size. Cantor called these countable and uncountable infinities respectively. And in fact, there are many more uncountable infinities which are even larger.
That was
Cantor's work was just the latest blow to mathematics. For 2,000 years, Euclid's elements were considered the bedrock of the discipline. But at the turn of the 19th century, Lobachevsky and Gauss discovered non-Euclidean geometries. And this prompted mathematicians to examine more closely the...
Did these guys even have calculators? At the time, these are old motherfuckers, man. Did these guys just take paper and they drew like the little symbols and little things and they just did fucking manually, dude? Like, what did you have to divide a big ass number? Did they spend like 8 weeks, like fucking 6 months doing the fucking drawing it down? No shot they did.
And they did not like what they saw. The idea of a limit at the heart of calculus turned out to be poorly defined. And now Cantor was showing that infinity itself was much more complex than anyone had imagined.
Funny. Okay, sorry, man.
In all this upheaval, mathematics fractured, and a huge debate broke out among mathematicians at the end of the 1800s. On the one side were the intuitionists, who thought that Cantor's work was nonsense. They were convinced that math was a pure creation of the human mind, and that infinities like Cantor's weren't real. Henri Poincaré said that later generations will regard set theory as a disease from which one has recovered. Leopold Kronecker called Cantor a scientific charlatan and a corrupter of the youth, and he worked to keep Cantor from getting a job he wanted. On the other side were the formalists. They thought that math could be put on absolutely secure logical foundations through Cantor's set theory. The informal leader of the formalists was the German mathematician David Hilbert. Hilbert was a living legend, a hugely influential mathematician who had worked in nearly every area of mathematics. He almost beat Einstein to the punch on general relativity. He developed entirely new mathematical concepts that were crucial for quantum mechanics, and he knew that Cantor's work was brilliant. Hilbert was convinced that a more formal and rigorous system of mathematical proof based on set theory could solve all the issues that had cropped up in math over the last century. And most other mathematicians agreed with him. "No one shall expel us from the paradise that Cantor has created," Hilbert declared. But in 1901, Bertrand Russell pointed out a serious problem in Cantor's set theory. Russell knew that if sets can contain anything, they can contain other sets, or even themselves. For example, the set of all sets must contain itself, as does the set of sets with more than 5 elements in them. You could even talk about the set of all sets that contain themselves.
Okay.
But this leads straight to a problem. What about R, the set of all sets that don't contain themselves? If R doesn't contain itself, well, then it must contain itself. But if R does contain itself, then by definition, it must not contain itself. So R contains itself if and only if it doesn't. Russell had found another paradox of self-reference.
Oh my god.
And he later explained his paradox using a hairy analogy. Let's say there's a village populated entirely by grown men with a strange law against beards. Specifically, the law states that the village barber must shave all and only those men of the village who do not shave themselves. But the barber himself lives in the village too, of course, and he's a man, so who shaves him? If he doesn't shave himself, then the barber has to shave him. But the barber can't shave himself because the barber doesn't shave anyone who shaves themselves. So the barber must shave himself if and only if he doesn't shave himself. It's a contradiction. The intuitionists rejoiced at Russell's paradox, thinking it had proven set theory hopelessly flawed. But Zermelo and other mathematicians from Hilbert School solved the problem by restricting the concept of a set. So the collection of all sets, for example, is not a set anymore, and neither is the collection of all sets which don't contain themselves. This eliminated the paradoxes that come with self-reference. Hilbert and the formalists lived to fight another day, but self-reference refused to die quite that easily. Fast forward to the 1960s, and mathematician Hao Wang was looking at square tiles with different colors on each side, like these. The rules were that touching edges must be the same color, and you can't rotate or reflect tiles, only slide them around.
Oh no, not again.
The question was, if you're given an arbitrary set of these tiles, can you tell if they will tile the plane? That is, will they connect up with no gaps all the way out to infinity? It turns out you can't tell for an arbitrary set of tiles whether they will tile the plane or not. The problem is undecidable, just like the fate of a pattern in Conway's Game of Life. In fact, it's exactly the same problem. And that problem, ultimately, comes from self-reference, as Hilbert and the formalists were about to discover. Hilbert wanted to secure the foundations of mathematics by developing a new system for mathematical proofs. Systems of proof were an old idea going back to the ancient Greeks. A system of proof starts with axioms, basic statements that are assumed to be true, like a straight line can be drawn between any 2 points. Proofs are then constructed from those axioms using rules of inference, methods for using existing statements to derive new statements, and these are chosen to preserve truth. If the existing statements are true,
this is gonna lose me.
then so are the new ones.
It's gonna lose me.
Hilbert wanted a formal system of proof, a symbolic, logical language with a rigid set of manipulation rules for those symbols. Logical and mathematical statements could then be translated into this system. If you drop a book, then it will fall would be A then B. And no human is immortal would be expressed like this. Hilbert and the
Okay, I'll
formula...
skip. Okay, guys. I'll skip. Everyone's gonna get tired. It gets worse. Yeah, it's okay. Okay. Jesus. The Chad's being impatient. I want to watch what Chad's being impatient did. Okay, we'll learn it.
wanted to express the axioms of mathematics as symbolic
I think
statements
it's a
in a
good video.
formal system, and set up the rules of inference as the system's rules for symbol manipulation. So Russell, along with Alfred North Whitehead, developed a formal system like this in their 3-volume Principia Mathematica, published in 1913. Principia Mathematica is vast, a total of nearly 2,000 pages of dense mathematical notation. It takes 762 pages just to get to a complete proof that 1 + 1 = 2, at which point Russell and Whitehead dryly note, "The above proposition is occasionally useful." The authors had originally planned a 4th volume, but unsurprisingly, they were too worn out to complete it. So yes, the notation is dense and exhausting, but it is also exact, unlike ordinary languages. It leaves no room for
Guys, at this point, they didn't have calculators.
errors or fuzzy logic to creep
There's
in.
some fucking enchantment
And
table,
most
dude.
importantly, it allows you to prove properties of the formal system itself.
There were 3 big questions that Hilbert wanted answered about mathematics. Number 1, is math complete? Meaning, is there a way to prove every true statement? Does every true statement have a proof? Number 2, is mathematics consistent? Meaning, is it free of contradictions? I mean, if you can simultaneously prove A and not A,
then that's a real problem because you can prove anything at all. And number 3, is math decidable? Meaning, is there an algorithm that can always determine whether a statement follows from the axioms? Now, Hilbert was convinced that the answers to all 3 of these questions was yes.
At a major conference in 1930, Hilbert gave a fiery speech about these questions. He ended it with a line that summed up his formalist dream. In opposition to the foolish ignorabimus, which means we will not know, our slogan shall be, we must know, we will know. These words are literally on his grave. But by the time Hilbert gave this speech, his dream was already crumbling. Just the day before, at a small meeting at the same conference, a 24-year-old logician named Kurt Gödel explained that he had found the answer to the first of Hilbert's 3 big questions about completeness. And the answer was no. A complete, formal system of mathematics was impossible. The only person who paid much attention was John von Neumann, one of Hilbert's former students, who pulled Gödel aside to ask a few questions. But the next year, Gödel published a proof of his incompleteness theorem, and this time, everyone, including Hilbert, took notice.
Interesting.
This is how Gödel's proof works.
Gödel wanted to use logic and mathematics to answer questions about the very system of logic and mathematics. And so he took all these basic symbols of a mathematical system, and then he gave each one a number. This is known as the symbol's Gödel number. So the symbol for not gets the number 1, or has the Gödel number 2, if then is Gödel number 3. Now, if you're expressing all of these symbols with numbers, then what do you do about the numbers themselves? Well, 0 gets its own Gödel number, 6. And if you want to write a 1, you just put this successor symbol next to it. The immediate successor of 0 is 1. And if you want to write 2, then you have to write SS0, and that represents 2, and so on. So you could represent any positive integer this way. Granted, it is cumbersome, but it works, and that is the point of this system. So now that we have Gödel numbers for all of the basic symbols and all of the numbers we might want to use, we can start to write equations. Like we could write 0 equals 0. So these symbols...
Okay. Chat, I'm willing to do it on chat. If you want to go finish it, you go knock yourself the fuck out, dude. I'm skipping this. I'm like, in chat, I'm skipping this shit.